Good evening, everyone, and very warm welcome to all of you. On behalf of SkySkill Academy, I'm really glad to have you all here for day one of our faculty development program on advanced electric vehicle diagnostics and simulation. Thank you for taking the time to join us. Today's topic is extremely relevant, especially because electric vehicles are no longer just mechanical systems. They're highly software driven and data driven systems, and diagnostic has become one of the most critical skills for engineers working in this space. So, when we talk about AVs in classrooms, we often focus on motors, batteries, and controllers. But in real life, one of the biggest challenges fault detection, fault isolation, and understanding what the vehicle is actually trying to tell us. So, day one is all about how EV diagnostics has evolved from traditional diagnostic approaches to modern web-based and data-driven methods. So, just a quick introduction about SkySkill Academy. I'm not sure how many of you are aware of SkySkill Academy. So for those who are joining SkySkill sessions for the first time, so at SkySkill Academy, we work closely with engineering colleges, ITIs, universities to set up training facilities or EV, solar, IoT, and advanced technological labs, and also to train both students and faculties on industry relevant systems. So our focus is very simple. It's making sure what is taught in classrooms connect directly to what happens to the industry. So I have a short presentation before we get into technicals or with our keynote speaker today, Mr. Sajid Kumar. I have a small presentation about a company which you can delve into. Probably we'll discuss more at a later stage or towards the end of it. Okay. So Sky Skill Academy has come a long way from starting from 2018, where we were known as Skywriter Institution, to 2023, where we rebranded ourselves to expand our divisions, not just into training program. We started as a skill development platform, or we are currently India's premier platform for skill development and employment in technologies, whereas we have also started getting into product development, research and development as well. So we vision to basically revolutionize education and build a workforce that is ready for what is coming in technology tomorrow. So we have 100 plus certification courses across multiple technology domains, trained around 2 lakh plus students across 7 plus countries, not just in India. We have 600 plus institutional partners, 30 plus industry collaboration with leading global corporation, 90 plus success rates across all programs. And we have successfully placed from our job leading programs, 1,000 plus students. Moving ahead, we have done various partnership. Most of it comes with various institutes, premier institutes, or with organizations. Whereas we have focused with E&ICT Academy, IIT Kanpur, for joint development of online courses in electric vehicle, embedded systems, CATIA, SolidWorks, autonomous vehicle, and other softwares. We also have partnered with E&ICT Academy, IIT Guwahati, and joint initiative to improve technological education and research and innovation into the partnership in various domains similar to what IIT Kanpur has. So now SkySkill is an initiative on another vertical where we are focusing on building labs. These labs are Sector Skill Council approved labs, which focuses on creating technologies, creating training support for students so that students can get hands-on practical. So why this SkySkill Labs is something that we have pitched in is because one, this is Sector Skill Council certified. So we have partnered with Automotive Skills Development Council to get an approved or affiliation of our labs. We have 65 laboratories currently at this point across various states in India, including various engineering colleges, IITs, NITs, as well as with various foundations into the technology of AI, digital twin, simulation-based learnings, solar, drones, and we have 30 plus hiring partners which directly link us to placement support. And complete support will be offered starting from your setup to placements to further collaborations. And this solution is customizable, so you can have complete assurance that these labs can be upgraded in future as well. Moving to, I would love to introduce, now like to briefly introduce our trainer for today, Mr. Sajid Kumar. He brings over 2 decades of expertise in automotive engineering, system modeling, and skill development to his role. He holds a BTech in mechanical engineering from PSG College of Technology and has earned certification in instructional designs and learning effectiveness from LinkedIn. He During his timelines or roles, he is a chief technology officer at TrainLab Technologies, focusing on e-mobility, ADAS, Industry 4.0, and staffing of or adjunct faculty at BITS Pilani Hyderabad WLP program since 2018, teaching IC engines, calibrations, and system engineering. He recently delivered a guest lecture on engine calibration as also a technical advisor at AIC, CIIC, Startup Incubator for Smart Mobility. So his background includes hands-on experience from race cars transitioning to AI-driven automotive solutions like Gear Merit and leading workshops on EV design and calibration. So he develops virtual labs, boot camps, bridging academia industry gaps, ideal for FDPs on EVSkillLab. So, Sajid sir, it's now my pleasure to invite you to address us.
Right. Thanks a lot for the intro, Suchi. Um, Hope I'm audible. Yes, I can see myself.
Yes.
So, right. Um, so am I able to share my screen? Yes, I think I'm able to share my screen as well. Right. So thanks a lot for that. So I think we can quickly start with whatever I have over here. Right. So before we start, right, I would just, I mean, I don't usually use PPTs. Like I'm more would love to keep it fluid, right? So I would just like to take maybe just a couple of minutes to tell you a little bit more detail about what exactly it is that I do. I mean, I know Suchi has explained, but in a nutshell, and also to kind of set an agenda for what we're going to be discussing today, right? So I am what you would call as a cross-domain systems engineer, right? So the fundamental work that I do, 90% of the work that I do, I bridge core automotive domain, right? So this is where my core expertise is. I also understand embedded software really well, a little bit on the hardware, but primarily this is on the software. So this is both your traditional embedded software in C, C++, as well as your AutoSAR architectures, right? And of course, by extension, I also do quite a lot of model-based development. So this is basically the complete automotive software stack, which I've been working with for the last almost 15 years now. And again, the last 10 years, I've also been working on the ITES probably for the last 20 years. I mean, basically all full stack development and stuff. But I have a lot of expertise in machine learning, right? So probably you could also call it AI, right? So though AI is probably a wrong word to use, it's all machine learning models. So I kind of understand machine learning as well. So, in a nutshell, the work that I do on a daily basis is I translate things for teams working on different of the domains, right? So, I kind of tell them how you could deploy a machine learning algorithm onto an embedded hardware, or I tell them how do you build a algorithm to control an automotive control unit or something like that. So that is the areas in which I work, and I do primarily consulting in the same areas, right? So this is what I'm gonna, I'm gonna kind of bring to the table today, and what we are going to be talking about is a very interesting topic. This is diagnostics, right? So I've spent pretty much my entire life working with diagnostics. I worked on diagnostics from a aftermarket perspective. I've also worked on diagnostics from a OEM perspective. So I'm going to try and bring that kind of intro to whatever that we are going to be doing, right? So yeah, I mean, I'll probably just like start off with this, and I'll tell you the reason why I don't believe in PPTs is to kind of keep it a little flexible. I don't want to thrust a lot of slides and be done with it, right? So, anytime you want to stop me for any Q&As or something, please feel free to do so, right? So, let's probably start with understanding what diagnostics is, right? So what do you understand by diagnostics, right? Or why do you basically need diagnostics? So we'll probably start from there. I think that's a pretty good place as any for us to start with. So let me probably um, okay, what screen? Suchi, can you tell me which screen you're able to see right now? Is it the whiteboard or whiteboard? Okay, you're
It is
muted.
the whiteboard, sir.
It's the whiteboard. Yeah. Okay, great. So just give me a second, right? So I'm just gonna put something out here. Copy. Yep. So I want you to look at this particular image that I put out here, right? So it's not exactly a very expensive car or something, right? As far as the current generation goes, this is something like which you would call as the one of the entry to mid-level compact SUVs, right? The new Kia Seltos. So now I just want you to think about this particular car, right? And I want you to name one particular system, right? Any system, not a component, but a system. Just name any particular system in this vehicle which is purely mechanical, right? So when I say purely mechanical, it should not have any sensors on it, right? You can kind of take any particular system, and it has to be a system. It's not just a component, right? And just think if you have any such system which is purely mechanical on it, right? Just go ahead and like just think about it. There's a reason that I wanted to start from this particular point. So transmission, okay, so let me probably clarify it. Let's assume that we probably have the automatic transmissions, right? Suspensions, yes, on this particular car, maybe suspensions still remain mechanical. Maybe some of the body parts, right? So maybe we have this body part. You can't call this a mechanical because the doors you have this flush handles which pop out. So maybe the fenders, maybe your bonnet. I wouldn't even call the windscreen here because the windscreen in a lot of cars you have the HUD, the heads up display. You have the ADAS camera which sits on the windscreen. The bumpers have got radar. They've got active vents in there. They've got ultrasonic sensor. The braking system is completely driven with electronics. The ABS drives the electronics, right? So what basically happens is a modern day car, right? If you take and usually you have anywhere between 50 plus electronic control units, right? So now I don't want you to think an ECU is just a big box. It has to be like this. No, it's not just that. Anything which is kind of controlling a mechanical component or a sensor or something, you typically call it an ECU. So ECUs can be really small, the size of a matchbox. It can be really big, or in case of ADAS control units, it could be some really big microcontrollers, microprocessors, right? So our vehicles have become immensely complicated, right? And when it becomes immensely complicated, just imagine the number of people that you need to coordinate with. Imagine where these people are working. Earlier, probably most of them used to be working in a single location, but now the teams are truly global. They are very distributed, and even inside a single city, people are not probably coming to the office and working. They're probably going to be like working from home, right? So, does everyone have a sound problem? Should I check something from my side? Can someone confirm if the audio is okay?
Audio is okay. Not
Yeah,
an issue.
thank
Yeah,
you.
audio is okay.
Okay, thank you, thank you. Thank you. Right. So, the complications have kind of become huge, right? So when this becomes a lot of different things starts coming in, there has to be some way for us to understand if some component in the vehicle is going wrong, right? So it can be to tell us that something is going wrong while we are developing the vehicle, or it can be a problem like after we have developed the vehicle, we have sold it to the market, and then someone has to understand what is going wrong, and then they'll have to be able to repair it. Always come back to this thing. There is 100 million lines of code sitting inside the vehicle. There are 50 plus ECUs which are sitting in the vehicle, and probably there are going to be some 30 sensors, 40 sensors, and all of this complex thing is kind of working together, right? So this should kind of give you a motivation to start building some diagnostics application, right? So that's where we're going to start with. You understand the problem which we have, right? So now this diagnostics application, just to give you a background information about how it actually started, right? So when this started out sometime in the early 1990s, I mean late 90s or early 2000s, right? So 1990s, what first happened was in California, right? There is a emissions control body. We call it as CARB, CARB. So it stands for California Air Regulations Bureau. So they said, "Hey, you've been making cars, and we are still talking about IC engine vehicles, right? So we are not gone into the era of electric or something. This is the early 90s. So they said, we are selling cars here in California, but we don't want California to get spoiled and blah, 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 whatever it is." And they said, you'll have to kind of like make sure that your vehicles do not pollute, right? So they said that we don't want the vehicles to pollute, so you'll have to make sure your vehicles are not polluting. So this was the very first pollution control norms which came up, right? That was in the early 90s. So now the government is thinking, okay, we've told you not to like pollute, but how do you kind of ensure that we are kind of like making sure that you're still not polluting, right? So that becomes a problem. Just give me a second. Just give me a second. Right. So how do you know that the manufacturers are not cheating on pollution, or an individual car is not cheating on pollution? There has to be some way for the government bodies, for the government agencies to know if your car is polluting or not. So for the very first time, they said all the vehicles will mandatorily have a diagnostics application, right? And that diagnostics was called as onboard diagnostics, right? So what they said is, as a manufacturer, now you are responsible for making sure that your vehicle does not pollute. And the way that you will make sure that your vehicle is not polluting is by writing some software which sits on board. Basically means it sits inside your ECU, right? Engine control unit in those days. So it sits inside the engine control unit. It monitors all the systems, and okay, and this I'm talking about from a government perspective, OBD perspective, right? So OBD is always government. So just think of this like this. This initially started with your Californian bureau, but all the governments started using the same standards. So what they said is, anytime there is something which will kind of like cause your pollution norms to fail, right? So that type of failures alone, your onboard diagnostic system has to monitor. Okay, so understand this distinction. We're going to go into the more advanced diagnostics. So I think this is basically something which is very essential. So onboard diagnostics was brought forward by the government, and they said you will monitor pretty much any component and every component which might cause your vehicle to fail pollution checks. So that was called onboard diagnostics. So which basically meant onboard diagnostics will monitor pretty much everything on your engine, right? Anything connected to your engine, it will monitor. But it will not, onboard diagnostics will not monitor, let's say, brakes. Onboard diagnostics will not monitor, let's say, airbags, your supplementary restraint system airbags. It might not monitor audio system, head unit, or whatever it is. It is not going to monitor all of these things. Onboard diagnostics is purely with respect to engine. When I say engine, it means transmission, it means cooling system, it means lubrication system. So anything which can cause your engine not to perform optimally, it will monitor it. So this was good for a while, but after that, cars started becoming complicated, right? Using all the 100 million lines of code and stuff. So when that started coming up, manufacturers thought, okay, anyways, we have an onboard diagnostics which is sitting here. Why don't we expand it? Why don't we increase the diagnostics, and why don't we cover other systems? Like, say, for example, there is an airmatic suspension in a vehicle. A Mercedes Benz has got an airmatic, the air suspensions, or there is an ADAS system, right? So when you have these extra systems coming in, automotive manufacturers wanted to cover this also. But unfortunately, they could not cover this under OBD because the OBD happens to be an ISO standard, right? It's a standard. You cannot change it. You cannot just simply go change it. So now there are other systems also which are present in the vehicle, which manufacturers wanted to kind of control, and that was not being covered by OBD. So they came with a new way or a new method to kind of cover the other systems. So they called it as the unified diagnostics diagnostic services, right? So they called it as the UDS, right? So UDS became a protocol. It's an ISO standard as well, right? So what they decided was that, okay, hey, government guys, you mandate us to kind of do everything for engine. And see, the main problem is if it is with respect to the engine OBD, this has to be monitored by anyone, right? So which means anyone can monitor it, right? If anyone can monitor it, so then it basically means it is open access. You cannot control who accesses it. Anyone can access, anyone can check if pollution norms are met, anyone can basically do that. But whereas when it comes to the airbags or ADAS or brakes or something, they don't want anyone to access. They want only qualified people. They want only technicians to access it. They want only their own qualified engineers to access it. So UDS is basically a closed as well as a secure platform. Okay, so I just wanted to kind of wanted you to understand the background about what diagnostics basically means, because very frequently, whenever you go, you start talking to people, right, OEMs or something. So they'll talk about OBD, which is onboard diagnostics. They'll talk about UDS, Unified Diagnostic System. Now, a tool which helps you perform UDS services, right? We basically call it as the tool or tester, right? This would probably cost you about 1 lakh plus. I'm talking about IC engines. Whereas an OBD code reader, so we call it as code reader. An OBD code reader, you can get it for 500 rupees plus. You go to Amazon, you will get an OBD code reader. You go to Peak Can, they'll sell you something for 40,000 rupees, right? So that's a CAN interface which can be used for UDS or something like that. So Peak Can is 40,000 rupees. The other one is about 500 rupees. Both of them communicate with the car, but what basically is the difference with it? Why do you exactly need to have two different systems, right? So this is where the confusion starts. Number one. So we are going to be talking about that. Number two, right? Wow, how does this work when it comes to electric vehicles? Because electric vehicles do not have an engine, which means they are not mandated by the government to basically build any kind of a diagnostics in house. They don't necessarily have to have any kind of have a diagnostics in house, which means EV currently there is no requirement, there is no legislation which makes a diagnostic system compulsory, right? Now, this throws up a lot of interesting things because any small vehicle manufacturer, if you take India right now, any small vehicle manufacturer, they are not required by the government to put a diagnostic service inside. So most of them don't even understand what diagnostics is needed. They go build their vehicle, they bring the vehicle onto the road. So now you're driving an electric scooter or an electric bike or something. The bike has a problem. How do you know what's the problem? Right? So initially when they're a small startup, they think that, okay, I mean, you know what, we'll send a technician will go check with the multimeter or something like that, they can fix it. But what happens when you sell 1,000 bikes? What happens when you sell 10,000 bikes, a lakh bikes, right? So this is the biggest problem which is there in the market. There is no common standards for EV. So as far as IC engines were concerned, at least there was one common standard, which was basically like OBD, which kind of allowed you to diagnose any kind of pollution related problems with respect to IC engines. But now you don't have a common standard, right? So this is a very interesting area for research if you're interested. There is absolutely no standard, common standard for diagnostics in EV, which means anyone can come up and develop their own standards, right? So which basically means you can go develop your own standard, you can sell it to some OEMs, or if you actually do come up with a framework which is really advanced enough, people might be interested in probably purchasing your stack, right? So I think this should give you a pretty good idea about why I'm trying to talk about diagnostics in particular, right? So, in a nutshell, if you have not followed through, in a nutshell, there are two reasons. So, the first one is there is no diagnostics which is mandated for EVs, which means not many people have got an EVC, I mean, a UDS stack on the EVs. And second thing is, since no one knows what to do, everyone is developing their own stack. So, there is always a reason for a new stack or a customized stack or someone to adapt it or something like that, right? So this should kind of give you enough opportunities to kind of like either work with the industries, help them solve some diagnostics related problems or something like that, right? So now this is the basic reason why we are trying to talk about diagnostics. Okay. So I hope I've kind of made the reason behind this clear, the rationale behind it clear. So now I'm going to take another 6:30, right? I'm going to take another 1 hour. I'm going to talk about how exactly we could build this, how exactly you could build it, not we, you could build it, how you could do it as a learning exercise at your college, or you can kind of use one of our test tricks and develop this UDS stack, how you could work with OEMs, among other things. So, is there any questions before we move forward with this? Anything that you want me to stop and answer? UDS, OBD. I will do that. I have a
Yeah,
slide deck as well.
I have a
I will share the
question.
slide deck as well.
I have a question, Mr. Sridhar.
Yes, please.
See this. Are you going to touch upon the ASIL standards also as a part of
See, ASIL doesn't come in with this. ASIL is going to be on functional safety, so that's basically on the embedded software side. But probably like, I mean, I'll stop my discussions by 7:30, and we could probably the last 30 minutes during Q&As, I could take you through ASIL. I can give you a quick laydown on what functional safety. That's ISO 26262. I can probably talk about that. If you could please bring the question up again during the Q&A, I can take 5-10 minutes and speak about that.
Yeah, okay, thank you.
I have one question.
Yes, please.
There is certain sort of onboard diagnostics in the electric vehicle. Every manufacturer, I think, is having something. Because recently I encountered one problem
Mm-hmm.
that while I was going for charging, DC fast charging,
Mm-hmm.
there was some error from the charger side. Some communication error was there.
Mm-hmm.
And because of that, it was not taking any further DC charging, and my vehicle got stuck when I was having 0% battery.
Mm-hmm.
So I had to visit the repair shop.
So
That
I
is
believe you
the
have a
workshop.
Tata or a Mahindra?
No, I have a Windsor, MG Windsor.
MG Windsor, right? So the
Yeah,
big OEMs have it. So the
yeah,
people who don't have it are the smaller OEMs, startups.
yes, yes. Because the
Honda
fault was
doesn't have it.
cleared after doing the diagnostics only. They removed the fault. The
Mm-hmm.
flag was set.
Mm-hmm.
Some flag was set, so it had to be reset. And only after that, the DC charging was further accepted.
Right. So we'll I'll first explain about what this diagnostic stack is. And I'll also probably show you how easy or difficult that's going to be. I'll probably like talk to you about that as well, right? So that's what we're going to do next. I'll tell you why is it that I feel that there is a lot of scope for you to do some research activity in the field of diagnostics. We'll cover that. There's a lot of research activity in this, right? Okay, there's no regulations on EV. How is government approving the EV? See, there is a homologation requirement which is there, but unfortunately, homologation does not include diagnostics. The government is not saying you should have a diagnostic stack on the vehicle. They have various standards for motor testing, battery, and all of those things, but unfortunately, there's nothing for diagnostics. It is not at come, no one has a common standard. So, see, suppose you have an OBD tool, the 500 rupee OBD tool. You can go plug it in any vehicle made after 2000, 2000, right? The year 2000, until till date, any vehicle. Every single vehicle with an IC engine, petrol or diesel or hybrid will support OBD, right? I mean, which means all the manufacturers across the world, everyone follows the same standard with respect to onboard diagnostics. But UDS can be individual for every single manufacturer, but for EVs, there is no common standard as of now. So that's what I'm trying to tell you. Okay. I'm not sure why there is a audio problem. I seems to have a stable internet connection sitting right next to the router. So probably the problem could be from your end as well. I'm not really sure, but
Yeah, we are hearing properly. No
right?
issue.
Okay, okay, thank you. Right. Okay, so now let's get into it, right? So we've understood that there is something called UDS. So now I'll try to kind of give you a very big picture about how this UDS basically works. Very simple picture, right? And once I do that, then I'm going to kind of tell you how the whole stack is built and works. I'll probably do that, right? So in order to do that, the first basic thing that we'll need to understand is what is diagnostics dealing with, right? So diagnostics is dealing with some kind of a signals, right? And where can the signals come from? It can either come from sensors or it can come from actuators, or status of actuators can also be signals, right? So that's basically the primary understanding. Now, this signal per se can be analog, it can be voltage analog, or it can be digital. But we are not bothered about it, right? So whatever comes from the sensors, actuators, right, whether it is analog or digital or whatever it is, all of these signals will anyways, end of the day, it will end up getting into a control unit. And once it gets into the control unit, right, all that will come out of it, irrespective of whatever the signal originally was. Let's say that this is the gateway or this is the vehicle control unit, right? I'm not going in for any other terminology. This is the vehicle level control unit. This is the master control unit. So now any type of a message which has to go from any control units to the vehicle control unit, it basically goes over a two-line network, right? So we call this as the CAN bus, right? So there's the CAN high, there is the CAN low. I mean, it's a twisted pair, but you basically understand this, right? So what this means is that it's not just going to be one single control unit which is sending out. There could be multiple control units. That's what a bus topology is. There's going to be multiple control units sitting on the same network. They're all sending out the messages. Everything is going over CAN, and the vehicle control unit is receiving it. It's processing whatever is happening. Okay. So the understanding is that whatever comes out of sensors and actuators, we are not dealing with the signals at the physical layer, right? So the seven layers over, say, communication layers, let's go down to the bottommost layer, the physical layer. We are not working at it at the physical layer. What we are allowing to do is we are getting these signals, we are kind of converting that into your CAN signals, CAN messages, and CAN signals. So when it goes into the CAN layer, so CAN is probably what, the fifth layer, sixth layer, something like that, right? It's one of the higher level layers. It's not the bottom layers. So all we understand is anything that we deal with inside here, these are all CAN either messages or signals. We are not talking about this, all data, right? It's all purely data. We are not talking about physical signals here. We are purely talking about data here. Okay, so the first thing is that's where we are getting all of these things from. It's all the data that we are getting. So now inside the vehicle control unit, right? So your ECU, right? ECU, VCU, whatever it is, inside this, we'll have some kind of a software architecture, right? You'll need to have software architecture. You'll need to have different components, right? We call it software components, SWC. So this can be a regular layered architecture, or it can be an AUTOSAR layered AUTOSAR architecture. Let me not jump in too much into the architecture per se. That's a different topic for another day. But let's assume that we have either a layered architecture or we have an AUTOSAR architecture. I'm sorry, like if some of you are not from an embedded software's background, or if you are, if you would like to listen, I mean, want me to talk about it, we can probably do it during the Q&A. But I'm assuming there's going to be a mixed audience here, so I'm kind of abstracting these concepts. I'm not getting into how exactly it is there. All I'm telling you is inside the vehicle control unit, there is going to be various software components which is dealing with various functions and things. And over here, there will be one piece of software which is called as DEM, right? So DEM stands for Diagnostics Event Manager. Right? So don't think that it's a physical thing. It's just a function. It's a software function. It's a C function. And that's called as the DEM, which stands for Diagnostics Event Manager. Now, what will this DEM do? Right? So there is a DEM, there's a DCM, Diagnostics Communication Manager, but let's purely look at the events alone here. So the function of DEM is purely to understand what is happening with the CAN messages, and via the CAN messages understand what is happening with the sensors and actuators, right? So the DEM is a piece of software function. I can show you some examples of these software functions if you want, but the DEM is basically a software function. Now what this DEM is going to do is, let's kind of like expand it out here. So let's say, I mean, we are only getting CAN signals, right? So it can read a lot of CAN signals. It's not physical IO, it is just messages which is coming in. So any message that comes in, it can basically read those messages. Okay. Technically speaking, there is something called as an RTE layer which sits here, right? So it's not directly reading the CAN messages, but there's an ISO-TP, CAN-TP, right? It comes through there. There's an RTE layer, but let's assume that we are able to send the signals. It is able to read it, right? So what do you mean by reading? It's like basically a global variable, right? And you just read that global variable from inside this function. So now once it reads a signal, you will have to tell the diagnostics event manager what each signal is supposed to represent. Okay. So basically what I mean to say is there are rules written here. I'll show you practical examples of this, right? I'll show you a very simple example of how this can be built. But what I want you to understand is signals come into the system. There are rules, and based on the rules, this will be able to say whether there is an error or not. Extremely simple, right? So I'm just gonna unshare this. Let me just see, like, if I have my simulator running. I just built a small interactive simulator. So let me check if I'm able to share that with you. I've unshared the screen. I'm gonna reshare it. So this is a part of what we have built, right? So this is not kind of the full diagnostic stack, but this is basically a part of whatever we have built. So this is a diagnostic simulator, right? So now let me, I'm just writing some mock signals, right? I don't have a car with me here. So I've just put a mock signal here. So now you see I'm receiving the CAN signals. Am I physically connected to the car? No, I am not. But my piece of software, it is running on my laptop here, and it is able to receive CAN signals. Now, since CAN signals are informational, right? It is informational, it is not at the physical layer. Sorry, this can basically come from some testing that I've done. I've written it in Rust, so it's basically getting the signals here. Or I can actually bring it from a physical adapter. I don't have a physical adapter. I don't have a car. I'm sitting here inside my house. So I don't have that, right? I don't have the adapters, but I do have mock signals running. So this is how the whole software is going to work. So the software does not care whether your signal is coming from a real car or it's coming from a simulation. Wherever it is, it can. Now, how do you understand this? Right? So what you can think is you build a diagnostic software, you build a MATLAB Simulink model. You're going to learn about MATLAB Simulink and modeling tomorrow, I guess. Siddhant, my colleague, would probably be talking about it. So you can build a model in MATLAB Simulink. You can convert all of those signals virtually into a CAN signal. You can feed it to a diagnostic stack and you can build your diagnostics algorithm. Right? So how cool is that? You build an FOC algorithm, you build an advanced diagnostics rule where just by probably monitoring the back EMF, you would be able to probably predict what the motor is doing. You'll be able to predict the torque. You'll be able to predict torque degradation, something like that. Or if your interest is in the battery domain, how cool would it be if you can predict the current ramp up or the as a function of current, you can kind of monitor how much the temperature ramp up would be. So anytime the temperature goes up beyond whatever your model says it should, then you know that your internal resistance is going up. You could pop up an error, right? So this is basically the research areas that you can have, because UDS, right, is not exactly like a physical layer. It just takes informational objects. You can basically work with any signals. Now I'm working with Python or Rust. You can do it Python, you can do Rust, you can do probably like MATLAB Simulink. But why would you want to do Python, right? So remember all your your mathematical models, all your machine learning models. Every single machine learning model and probably your digital twin is going to be written in Python, right? So which means it can also work with Python, right? So that's the beauty of it. You can get your data from anywhere. And then we have the DTC rules, right? So I said there are rule-based DTCs. So all you do is you select a particular signal, right? I think this is not completely live. Yeah, okay. So you select a particular signal, break position. Break position is 0, or okay, let's use battery voltage. So you say, okay, battery voltage, there is an error you're creating. We are calling it as battery voltage low. We'll have to give a code for it, right? It's an ISO standard. So we'll say battery is in the battery system, so we'll give it as B. And remember I said there is no standards which are defined. So I can go define my own standards. In fact, I can just say Sajid Kumar underscore 1234, right? I can say, hey, this is the thing. I am developing the code, you put mine on it. I mean, it works. Electric vehicle, it works because no one has defined a standard. You're free to use it. You can sell your own software, your own tool. The manufacturers will have to work with yours, right? So that's kind of the beauty here. And then you say, okay, what is this happening? It says battery voltage is below the prescribed limits, right? And when should this be triggered? It not above, it's going to be less than, right? What voltage can you do? Right now, the battery voltage is 366. So let's assume that if it falls below 350 voltage, then this particular error has to be triggered, right? The tool here is not completely full-fledged. I'm not on the development system. I'm sitting with my laptop here. So usually when it is functional, you click it, a new rule will be created here, but now I get an error. I understand because I'm not on that particular system here, right? So in a nutshell, this is what UDS is. But what I'm showing you is not exactly UDS, because UDS is supposed to sit inside your ECU. It's supposed to be written in C, C++. It's supposed to use layered architecture, which means it's extremely complicated for you to visualize. But I'm just trying to visualize a off-board diagnostics, which uses a similar thing, which you can use for your learning, right? So this part of the, some of the tools which we give for understanding about UDS. So that's what I've shown you. So remember, there are two parts. First part is signals has to come into the system. How you feed the signals into the system is up to you. You can do it from MATLAB, you can do it from Simulink, you can do it from EMISIM, you can do physical systems. You can take an RC car, like a remote control car. You can put a small data logger, extract the values from the RC car. You can feed it into the UDS system. You can allow your students to build something. You can build something similar for, let's say, a genset. You can do it for any particular machine. You can build a diagnostics. It's all the same. Principles remain the same. Once you understand that, you can basically go build it for pretty much anything else, right? Signals is the first thing. Then you have the rules. Once you have the rules, whenever there is a problem, it will start throwing up error codes, right? So let me see if error codes. Yeah. So it basically says 0, 1, 2, 3, 4. There is something which has come, and you see the status has changed, right? Earlier it was what did it say? Let me clear it. So these are all the way it is. Okay, it says pending. And if it's repeated 2 times, 3 times, then it will convert into confirmed, right? So 2 times it's repeated. So then it's become a confirmed error code. Now an error code is logged, right? So at a very high level, this is basically what your diagnostics is, UDS is. But are we happy with this, right? So the question is, are you going to be happy, right? As probably researchers, are you going to be happy? I would assume no. If you're happy with it, then you would probably not be sitting here listening to it. You can probably like just, I mean, no point, right? Someone's already done it. Bosch has done it for the last, I don't know, 25 years. And there's nothing new to be done with this as how they are doing it. But this is where things starts getting interesting, right? So what we are currently working on is we kind of like built out a diagnostics layer here, right? So what we are now trying to do is we are trying to connect to the vehicle. We are trying to extract the data from the vehicle as scan signals. We are trying to like build rules. And this rule-based engines, I can basically, I mean, I just have some, you know, refresh DTCs. Okay, just give me a second. Coolant pump. Yeah. Yeah. So what I'm trying to do is I'm just trying to like build up an interface where I can take this and I can basically feed it out into a large language model, an LLM. So hence the name AI here. But it's not just like I'm kind of like feeding everything manually. I'm going to chat GPT and typing out. It's basically that it can start speaking to the car. Mr. Sahil, you have your hands raised. Is there a question? Um,
Question. Is this program more about like developing the diagnostic process and tool, or it is also we will focusing on the application part?
so could you be more specific on the application part? I'm going to cover a couple of applications. So is there anything specific you want me to cover? I can take your use case for it.
No, no, sir. Just I want to take an idea, like if this workshop is really important to me or not. Like I am from a EV service background,
Okay.
so would this
Okay. Okay. Which vehicles do you work on? I mean, just to give me an idea, hint.
like on the electric buses?
Okay.
So
Okay.
that is
Okay.
service engineer.
So I mean, see, there's a lot of specifics that I can probably share with you, which I might not be able to do in the workshop, but you could always reach out to us through our team. So now, let's say that you have a battery overheating problem, and suppose you work in the R&D, then you're going to go with your Busmaster or Pecan or something, and you're going to manually monitor your signals to kind of figure out what is happening, what is going wrong, right? So that is basically how you probably do that. But I'm going to show you a way in which we have tried to solve it using machine learning algorithms, using something called as knowledge graphs, and using the final layer is the LLM based inference layer. So this is a patent pending application which we have, and it is not purely theoretical. This is basically being used in a EV small commercial vehicle manufacturer based out of Chennai. We are also like doing a prototype for it for a Dubai-based EV two-wheeler manufacturer as well. So I don't mind sharing the details how we have built it, but probably in the workshop, I'll just tell you the fundamentals of how this works, how you probably like configure it. I might not be able to get into the machine learning part of it. It will kind of like need a separate session on its own, right? But if there's anything specific that you want me to go over or something, I'll see if I can take it during the Q&As. Is that right?
Right.
Sajid sir, may I interrupt for a bit?
Yes, please.
Yeah. So, professors, I just wanted to let you all know that if anybody is having any questions or doubts, they can drop the questions in chat so that we can take as many questions as possible by the end of the session. If that's all right with you, Sajid sir.
Yeah, perfectly fine. Perfectly fine.
All right. Thank you all.
Thank
We
you.
can
Thank you.
we can proceed, right? Yeah.
Thank you. Yeah. Right. Okay, right. Okay, so this is basically the just to give you a physical idea about how the UDS stack works. So now let me go back and let me get back to our discussion, right? So we've seen signals, we've seen rules, and we kind of like see how that becomes an error or not. But how exactly are the signals being interpreted? How exactly are the rules being interpreted? Is it just that it has to be less than equal to? Is it that simple, or do we have more complicated rules? We'll kind of like just look a little bit into that, and then we'll go into the UDS stack per se. We'll see what the UDS stack is, how it is built. We'll kind of get into that, right? So I'm just trying to take it one step at a time. So now, how many CAN signals would you probably have in a vehicle which might be relevant? I don't know, maybe for an electric vehicle, maybe 50 to 60 CAN signals, right? The same thing if it comes to an IC engines, maybe you'll have the full CAN. If you take, there's going to be like 1,000 plus signals which comes in an IC engine vehicle. Electric vehicles, small electric vehicles, at least the ones which are not passenger vehicles, the number of signals are less. But if you go for passenger vehicles, if you go for vehicles with ADAS and things like that, then even that it goes to 1,000 plus, 5,000 plus signals, because every single thing is being transmitted out over the canvas, right? So I just want you to kind of have that in mind. So now we kind of come to the next part. So what exactly are the rules, right? So we'll need to look at. So typically you will define the rules in a couple of different ways, right? So let's say that you have a sensor signal, right? So the value of the signal. So you would kind of have an upper bound and you will have a lower bound, right? So you will define this as either a lookup table, or you'll define it mathematically, whichever way it is. You will define a bound within which your sensor signals will have to sit. Then what you do is your DCM, right, DEM, it starts monitoring, right? So this is what it is monitoring. It's not actually plotting, right? It's just monitoring where it is. So now if a signal starts out here, then it's just normal. But gradually what happens is over a period of time, if the sensor signal starts going out here, then we call this as aging, right? Over a period of time, the sensor ages, the sensor becomes old, and as it ages, it starts going towards the upper bound or towards the lower bound. So now when this happens, let's say it is the oxygen sensor. Now oxygen sensor, maybe once it is 3 years old, 4 years old, it starts moving upwards. Then you understand that it has become old, you start compensating for it. It is still not an error, but you need to compensate. Whereas because of an error, maybe a short circuit or whatever it is, because of an error. Now, if this starts going out of the bounds, right? So, what will you do? Suppose it goes up, it comes back. It goes up, it comes back. Technically, it is an error, but when do you call it an error? You wait for some 3 or 4 cycles, you see that it is continuously going up, or if it is come back. If it is come back, then you don't register it as an error. But if this continues somewhere here, then this triggers an error, right? Or if it goes below, then this triggers an error. So you define an error, not just equal to, greater than, or less than. You have an upper bound, you have a lower bound. You say how many times it can go above the bound. Sometimes it will be okay if it goes below the lower bound, but it cannot go above the upper bound. So there are a very complex set of logic which you can define, and you can say declare an error. Now this error will be called as a DTC, diagnostic trouble code. Okay. So now this DTC is what you call it as. P is for powertrain, U is for body control, maybe C is for chassis, B could be for battery systems. So there could be various, an alphabet which starts with it, and then there is a 4-digit code. So this 4-digit code is usually defined by the manufacturers. So which means Maruti Suzuki might have different codes, BMW might have different, Audi might have it different. It is not exactly uniform. It can be whatever it is, right? So this is basically how the diagnostics event manager works. It monitors the signal and it basically throws out an error. Now, what this means is that any type of a logical error, right? So most of the times these are errors. If there are logical errors, this might or might not be captured by your diagnostics event monitor, right? Not captured by your diagnostics event monitor. So what it means is sometimes there could genuinely be something wrong with the vehicle, and if you have not thought about all the rules, you will not throw up an error code, which means it is perfectly possible that a vehicle is faulty, vehicle is not working fine. You take it to the workshop, they plug in a scanner, no error will come up. There are definitely things possible like that. Like, let's take for example, you're monitoring the motor's voltage alone, okay? And let's say that the bearing in the motor has become weak. So now the motor will kind of like start like making some noise. There's going to be reduced performance. But if you go and take your error codes and check, there might not be any errors which have popped up. Why? Because you're only monitoring your voltage, you're not monitoring the RPM, you're not probably doing a lot of other things. Whereas when you come to OEMs, let's say Hyundai, for example, or BYD or BMW, they would probably monitor the current, they'll monitor the RPM, they'll monitor the rate of climb of RPM, and then they'll not have a equal to greater. They'll also have a lookup table which will say, hey, if the motor is drawing so much of current, then the RPM climb has to be so much. If it is not happening, then you know that there is a torque degradation. So if there is a torque degradation, probably put up an error saying motor fault, or motor bearing fault or something like that, right? So it is possible to build very complex systems. It is possible to do very simple systems as well. So how much of an effort goes in is typically dependent on the manufacturer. Now, again, why is this like an interesting area? Because you can kind of write algorithms, right? So algorithms can be developed in MATLAB or Simulink or Python or whichever platform it is, which can help you to diagnose these type of problems. There are a lot of these problems which manufacturers do not have a right way to diagnose. So when I say right way, there are two things. You cannot write a very complex linear equation and expect a microcontroller to solve. So this should be possible to run in a microcontroller. It should be something which is, if not in a microcontroller, it should possibly be running on a server, an IoT server or something, in which case it becomes an off-board application, right? So that is the first part, which is how does DEM work? How does diagnostic messages pop up? how do you basically know an error has come up or not? That is the first part of it. Now let's go to the second part. So someone was asking in the messages, do you have a tool which will support electric two-wheelers, four-wheelers, something like that? So now this tool is basically something which we call as a tester, because for an electric vehicle you're working with UDS, right? There is no OBD. There is only UDS, Unified Diagnostic Service. Now I said that if you're working with a UDS and there is a car manufacturer 1 and there is a car manufacturer 2, each one would have their own way of diagnosing, their own way of like figuring out if there's a problem or something like that. So which means you should basically have a tool which is compatible with that particular manufacturer. So if not, you will not get a standard UDS tool. So basically you will get a standard UDS tool for a Tata EV, right? You might probably get it for MG, you might get it for Hyundai, Kia, whatever it is, but you might not get something for, let's say, um, let's say like, I mean, I have a small company, maybe my own company, some XYZ company, or a Chinese, a two-wheeler or something, you might not get a tool which has a UDS stack on it, right? So more often than not, cheaper vehicles will basically not have a UDS. What do I mean by not have a UDS? Their vehicle control unit will not have this DEM stack. It might not have RTE stack. They might not even have a VCU at all. They would just have a motor control unit. They'll have a BMS, maybe just some basic CAN messages going to your cluster, and that's about it. So basically, you'll need to have this software present inside your VCU, and only then you can connect it with a tool. So the more cheaper brands that you have, right, for learning or whatever purpose, the chances that it might have a UDS stack inbuilt are very less. But does that stop you from teaching your students UDS? No, it is not, right? So what we can do is this will still have CAN, right? So you can use our UDS stack, right? You can feed the CAN messages directly into the UDS stack which we have. And I mean, you don't need a UDS tool here because the stack per se has visualizations over the web. So the web is basically the tool, right? So whatever the web page I was showing you, that's basically the tool. Or if you don't want the web, you want to have a tool actually, and you want to show it on an app or something like that, we can do that. We can port this out into an app and give you. You can put a tablet. You can monitor this as well, right? So the thing that I'm trying to tell you is the UDS is basically a piece of software. It's a C code. It needs to sit inside your VCU. If it is not inside your VCU, you are not technically going to be able to use a tester tool. Okay. Now let's go one step again further, and let's see, assuming that you have a tool, you're trying to connect to this car, how does this communication happen, right? So what exactly is going to happen? How are you going to be able to communicate? Let's try to figure that out. Okay. I hope you're clear with this still here, right? What UDS is, how does diagnostics even monitor work, right? And now we are going into how does the communication between the tool and the UDS stack, we are going to be looking at that. So now this is something which we call as server client communication, right? So what this means is that your car, right, or your electric vehicle, whichever it is, let's say that this is the Nexon EV, right? So the Nexon EV, it's got a vehicle control unit. So this becomes the server, right? So what is a server? A server is something which stores all the information, and a client is basically someone who can try to speak to the server. So it sends request, right? And it gets response. This is a client server interface, right? So the vehicle control unit is not going to communicate with the client or the tool, right? When I say client, this is basically the tool. It's not going to be communicating with the tool at all point of time. It will only communicate when the tool sends a request, it will send a response back, right? So it's like a WhatsApp group. So someone has to say, hey, help me out with this particular thing. And then I will reply saying, okay, here is the answer to it. I'm not going to be saying, okay, here is the answer, here is the answer, here is the, I'm not going to push, right? So that becomes a subscriber kind of a channel where like the ECU is pushing and then you subscribe to that particular messages. So that's a different type of a communication. This is a pure client server communication. You'll have to send a request, you will get a response back. Now comes the problem, right? What request do you send and how do you understand what response comes back, right? So now this is why I said you cannot have a universal standard because now Tata might say, when you send a request to me, you will have to first ask, or you might first have to say a passcode. There is a secret passcode which I will use. So only if you tell me the passcode, I will acknowledge you, and then we can start having communications. Kind of like a secret agent, right? So there is a secret question, there is a handshake signal, and then they start exchanging messages. And even when they exchange messages, suppose it's saying like vehicle speed, right? So this will say vehicle speed is 1425, right? Now, what in the world does 1425 mean? Is it 142.5 kilometers per hour or is it 14.25? Because all the CAN messages they kind of work on fixed point arithmetic, right? So they don't kind of like you will not know whether like what this basically means. So this could be actually be scaled by 1 by 20, right? Which means divide by 20. So approximately what this means is your speed is approximately 70 kilometers per hour. Could be something like this. There could be scaling factors, right? And one single message might have multiple signals. You know that CAN is basically packaged signals, right? So one CAN data frame, right? I'm just taking the data frame alone. It might have multiple signals. There could be speed here. There could be the kilometer odometer, right? There could probably be fuel efficiency figure which comes here. There could also be SOC which comes here. So you'll have to first know, once you receive a CAN data frame, you'll have to know where is the speed, where is the odometer, where is the fuel efficiency, where is the SOC. You'll have to know that as well, which means unless you understand all of these things, or in fact, Tata Motors has told you that, okay, this is how I'm packaging it. You get the speed, you divide it by 20, that's basically your speed in kilometers per hour, or that's the speed in meters per second, whatever it is, right? They'll have to tell you. Second thing is this whole message, it is not just simply going to come. It's going to have encryptions, right? So that encryptions is what I meant as passcodes. So we have something called as seed key pair. This used to be the earlier one, right? From next year onwards, there is cyber security which comes, which means you will properly have a hash algorithm, and any message which is communicated over the CAN bus starting from next year, 2027 onwards, it will be encrypted almost to the levels of like what credit card transactions, web-based transactions are encrypted, right? So you have a 256-bit encryption standard which is becoming mandatory on all vehicles. So that's cybersecurity, right? So once that comes in, things are going to be more difficult. So what this means is you cannot expect to buy a Tata Nexon and connect a CAN device to it and allow your students to monitor the CAN messages. You will not be able to do. Why? First one, there is a seed key which we'll need to crack. Or for all I know, maybe they've already implemented encryptions. I'm not sure about it. Next one, I'll have to know which CAN message to capture. And in that CAN message, where exactly is the signal that I need and what exactly is the scaling factor to basically extract that signal. I mean, for example, is this even in binary, right? I mean, not binary. Is it in hexadecimal, or is it in or is it in decimal, or is it in what number system it is in? I don't even know that, right? So there could be so much of layers to it. So deciphering a CAN signal is not all that easy. But once you know that, probably you can reverse engineer it. But in our case, what we do is we work with OEMs. So the OEMs I work with, they tell me, okay, this is basically the CAN message, this is how it is packed, this is how it is scaled. So we are able to retrieve from that. Okay, so now this is the UDS protocol. So it's a client server protocol. You send a request, there's a response which comes, but the protocol per se is not that simple, right? So there is a lot of sequence of messages which needs to be sent, right? So first you have the handshake, and then you have a mode, and then you have a keep alive message which goes, and then you send a request, and then the response, is it the right response or it is an error response? So there are various standards which goes into it. I'm not, for the interest of time and to keep the topic relevant, I'm not getting deep into UDS per se, but this is basically how the UDS works. Now let's again repackage it from the sense of bringing machine learning into it, bringing AI into it. Let's kind of try to repackage it. So what exactly are we trying to do? There is a car, right? And the car has got a lot of signals coming out on your canvas. So the first step that we need to do is we'll need to unpack the CAN messages, right? And once we unpack, there are a lot of things that we could do to analyze the signal, right? You should not directly take it and try to feed it into a large language model. It does not work. It's very difficult for the large language models to do it. So we need to kind of like pass it into something which the LLM can understand. So the first one would be rule-based diagnostics, right? Which we have already seen, or there could be a machine learning layer to it, right? A machine learning layer will kind of predict what the signal has to be, and if the signal is not exactly what it has predicted, then it kind of throws up an error. So then there is what we can call as a error consolidation, right? So both of this feeds in here, and now it can either be presented to the user, right? Or it can kind of go to a large language model, which can then present it back to the user, right? So this is the kind of stack that you would start seeing coming up in all the modern vehicles. So there are multiple reasons why this has to happen, because like I said, remember the very first discussion we had, 100 million plus lines of code, right? There is also going to be 50 plus control units which are going to sit, and the CAN bus per se, right? You will have powertrain CAN, you will have body control CAN, you will have comfort CAN, and you will also have diagnostics CAN. So there are so much of CAN lines which are present in vehicles, and then there are 100 million lines of code, which means there is so much of problems which can happen. There is so much of errors which can happen. And then there are 50 plus control units, each one bringing its own complexities. And to kind of add fuel to the fire, now we are also talking about something called as SDV, which stands for software defined vehicles. Right? SDV is software defined vehicles. You'll see a lot of people talking about it. So, what SDV basically does is it is converting your car into, let's say, an Android phone. Now, imagine your Android phone. You buy an Android phone and it does not come with a call recording function. So, are you going to be stuck without a call recording function, or can you just download an app and can you put call recording? Or let's take, for example, your Android phone does not have a large language model built into it. Okay, you don't have an LLM access. So what do? You download ChatGPT, you pay for a subscription, ChatGPT is on your phone. You want music, you download Amazon Music or Spotify or something, you pay for it, you use it. When you don't want to use it, you disable it. You want to watch movies, you have apps for it, right? Now, similarly, they're trying to convert cars into similar systems. So, what can happen is, suppose I buy a base variant car. Okay. Now, a base variant Kia Seltos, since we started talking about Kia Seltos, would probably cost 13 lakhs. The top of the line variant will probably cost me 23 lakhs. There is a 10 lakhs difference, right? But let's assume that this gets ADAS and a lot of things like that. So now what I can actually do is I can buy a base variant. I can drive it inside the city. I'm all good with it. whenever I'm going on a highway, right? Let's say that I'm going on a trip or something like that. So at that point of time, I can subscribe to ADAS features. I can subscribe to cruise control, right? Maybe I can subscribe to something like video in the car, or I can kind of like subscribe to more power, right? Maybe my car has got only 100 bhp, but when I'm going on a road trip, I want to have 150 bhp. I can subscribe. So why are all the manufacturers going this way? Because everyone wants to build a SaaS business. You would have probably heard about it, right? Earlier, Microsoft Office we had to purchase, and I'm pretty sure no one has ever purchased Microsoft Office in your life, right? So we would all like use cracked version and things like that. But now, thankfully, we have subscriptions. So you pay 500 rupees a month for your teams, then you get access to Microsoft Office as well. The biggest thing which I see is people are actually paying for Adobe, right? Earlier, I mean, I don't know, there was no concept of paying for software. We'll always get cracked versions. But now that subscriptions have come in, you can use it for 1 month, you can cancel it, you can use it whenever you want it. So everyone's going towards that, and automotive manufacturers want to do that as well. So it's all about remonetization, monetization in a different manner. So that's basically what has been driving this change, right? So when all of these things comes in, what's going to happen is your diagnostics becomes that much more important. Now, where you have an opportunity to get in and start working is you have domain knowledge already, right? You understand, let's say, how motors work, you understand how suspension works, you understand how batteries work. So now what you can do is you can basically have a test rig, right? Or you could have a digital twin of the particular system, right? So which we can help you build, we can supply this for you. And what you can now start also working on is you can research on some UDS packages, right? So you could kind of find out very innovative ways of finding out if a component is failing, if a product is gonna fail. It is either diagnostics, which is product has failed, or it is prognostics. It is not failed, but it will fail in the future. How do we prevent it from happening? Right? You can develop UDS packages. And what use is it going to be, right? Is it going to help you in any way? So of course, primarily research and papers, so this can definitely help in that. But if you are kind of like really good with it, so now what happens is you can enter into the SDV platform, right? So please remember what SDV is. It is the glorified app store which works on cars. So now imagine that you built an application which can probably like read CAN messages from the BMS, and it can predict what is happening to your battery, right? It can probably send out real-time data. Or you have probably a startup idea where you're collecting real data, you're pushing it to some server. So some companies paying you for this data, you pay the users. So you come up with an app where if people install the app in their vehicle, they get 1,000 rupees a month free of. I mean, you keep crediting them 1,000 rupees, right? You keep giving them 1,000 rupees to put this app on their vehicle. I mean, I'm just giving out some kind of an ideas for this, right? Or you have an app where users pay you 1,000 rupees a month, and in return, what you do is you do all prognostics for the vehicle. So your car is going somewhere, you tell them, will it make the trip? Do you have enough charge? Are you expecting any kind of a problems? Or if you have a problem, is it safe to continue? Should you stop? Right. So there are so much of things which you can do if you really understand how the diagnostic stack works. So now what you can simply do here is you can get CAN messages. This can be physical or virtual, or it can be like purely Python code, machine learning models. We can give you the UDS stack. You can develop your own algorithms which will sit in there. It is all plug and play, right? I showed you a web page, but don't think that there's too much of data which goes in. Nothing like that. It's pretty simple. You can just upload your algorithms in a certain format, and it starts performing the diagnostics. And this kind of takes you into the research side, or if you want to do some research specifically in the SDV side, you can do that. You can do prognostics, which is predicting when the failures will happen. Diagnostics, of course, can happen. You can also use this to build digital twins, right? And the most important thing is this is not just for EVs or ICE or not just for automobiles. You can build it for machine tools as well, right? You can build it for, let's say, medical devices. You can build it for, let's say, um, something like a windmill, right? So pretty much anything that you want to think about, you can build digital twins, you can build diagnostics, whatever your area of interest in, you can kind of expand this and you would be able to build this diagnostics tools for it, right? So I think I'm right on time, 7:26. I think I'll stop this with this. I know it has been at a very high level, but usually UDS and diagnostics is probably like a 8 hour lecture, which is good. 4 sessions that we'll need to go with it. So I've not got into the details, but let me just open up the questions and I'll take the questions one by one. But if you have anything else, you can probably drop the question into the chat box, right? So I'll try to answer the questions one by one. ASIL is something which I have not touched upon. So probably I'll just touch upon ASIL and then come back here, right? So when we are developing all of these functions and things in the ECUs, there are some special considerations that you need to take into account. So I'll probably please let me know if I'm boring you to death with this. I don't know if it is actually relevant, but if you find it boring, do let me know. I'll give a case study, right? So sometime in the early 2000s, right, Toyota was selling the Camry and Corolla in the US, right? So this particular car, they had a a serious problem, which Toyota did not acknowledge for a very long time. So they had abrupt accelerations, right? So imagine you're driving the car, you're going on the highway, suddenly the car starts to accelerate. You let go your feet off the throttle, the car is still accelerating. You press the brakes, car is still accelerating. It's accelerating at full clip, and even if you're braking, you're not able to control it. Cars were meeting with accidents, right? So what Toyota had done is they had brought in electronic throttle body. So which meant when you press the pedal, normal vehicles, there is a cable which goes and controls the throttle. But with now the EVs, with all the modern day cars, your throttle does not have any correlation to the throttle body. It is all drive by wire. ETB is drive by wire, right? So what was happening was that the drive by wire motor was getting stuck in the open position. So even if you let go of your feet, motor is stuck in the full open position, which means engine is pushing out maximum power. And if you try to apply the brakes, vehicle is not stopping. So what happened was there was a electromechanical component, right? Electromechanical also means there is going to be a software component you introduced in order for you to kind of have some benefits, which is basically emissions, right? Emission benefits would have been there. But now what happened was this function failed. And when it failed, there was a catastrophic effect, right? I mean, people lost their lives. A lot of people lost their lives. And finally, if I remember it right, Toyota paid some $2 billion or something in those days to settle it out. It was such a big catastrophic failure. So then the ISO people, the automotive people, they started thinking about, okay, we are building functions, but how do we make the functions safe, right? So how should a software function fail? How should a component fail? So they kind of like came up with a new branch of engineering almost, right? And they call this as functional safety. Okay. So functional safety, they say, is an assessment of risk in a system. Okay. Now, what is risk? If I ask this question, each one of you would probably give me a different question answer. let's go ask a 16-year-old boy what is risk, right? He doesn't know what risk is probably, right? They drive bikes without helmets. They drive at 100 kilometers per hour inside the city. They put their legs out, they zigzag, and they say it's a thrill, right? Whereas a more mature person would probably find it extremely risky. For someone who's used to investing only in maybe like government bonds or FDs, investing in stock market is risky, right? So there is no particular way that you can define risk in a normal thing, but automotive standards, they've kind of tried to define risk in a particular way. So they say risk is a product of three things, right? First one is what is the probability that a failure will occur? If a failure occurs, how is the controllability? Suppose you're not able to control, how severe is the problem going to be? Okay, three things. First one is how often will a problem happen? If the problem happens, will you be able to control it or not? Suppose you're not able to control, will it be severe or not? Right? So this is the functional safety analysis that people do. So I'm just gonna paste a picture here, right? So copy image. So this we call it as functional safety analysis, right? So this is called as the ASIL chart, which stands for Automotive Safety Integration Level, something like that. Just expanded. I don't remember that. So the first one is severity, exposure is probability, and this is controllability. So let's probably start with a problem. Let's say that we have an ADAS vehicle, right? And the camera has failed. So now you'll have to do an analysis. I mean, I'm not going to do a thorough analysis, but I'm just going to simply say, right? So now if a ADAS camera fails, okay, you're driving the vehicle on automatic driving or adaptive cruise control, and suddenly the ADAS camera has failed. And this particular vehicle does not have a radar or some lidar fallback. You only have a camera. So now suppose the camera has failed. What will happen to the car? Right. So now first thing what you do is you figure out how often will this happen, right? So which is E1, which is very low, or E4, very high, right? Can it happen often, or is it very rare? How does it happen? Let's assume that this is E2. There is a very low probability that a camera can fail, or let's say that E3, right? Because it can rain, it can have fogs, there are a lot of things which can throw your camera off. So let's say the exposure is pretty medium exposure, okay? Now if this happens, will you be able to control the car or not, right? So you're driving, and suppose you have taken your hands off the steering, you have fallen asleep. Will you be able to control? A quick question, right? So I would say C3, you will not be able to control. Why? Because your hand is off, you're sleeping, you're looking here, you're looking there. It is going to be C3, right? Very difficult to control. In case this happens, how severe an accident can happen? I would go with S3 because an accident at 100 kilometers can be S3. Now, S3, E3, C3, right? This gives me an ASIL rating of C. So which means it is a very critical problem. ASIL rating of D is the highest problem, whereas the lowest one is called QM. QM is quantitative methods or quality methods, quality management, right? So you don't have to necessarily define some functions to reduce this, but you just take care of the quality, it is okay. So now what will we do if it is ASIL C? I will say driver has to have hand on the steering, right? You also do driver monitoring. I want you to go check this, right? A modern day car, if you take your hands off the steering wheel, it will not get into adaptive cruise control. Even the Teslas, they used to earlier like sleep and stuff like that. But now, unless you have your hand on the steering wheel, it does not basically get into the autonomous driving mode. Similarly, if you keep your hands, if you're looking something like this, it will immediately start beeping. There are driver monitoring features which are present, it will start beeping. So what we try to do is, as we introduce more software into the vehicle, we should not make the vehicle extremely failure prone. We should kind of like think about what are the failures that can happen. We should try to think about how we can design this particular system so that even if failures do happen, it is failing in a safe mode, right? So, which is why an adaptive cruise control will only activate when you have your hands on the steering wheel and you're looking straight. If you're not, then it will not activate. Similarly, if you touch the brakes, okay, now let me come back here. How did Toyota fix this ETB? So they said the first condition for the electronic throttle body to work is brakes equal to off. Only if the brakes are off, it goes into the ETB loop, right? So this is like writing a condition while, right, brakes are equal to off, then execute ETB, which means your ETB, your throttle body will only function when the brakes are off. So even if you slightly touch the brakes, the throttle body will basically stop working. And they designed the throttle body so that it fails. If it fails, if the motor is jamming or something, there are extremely heavy duty springs which will close the throttle body. So a motor needs to basically like take a lot of current and then it has to open against the spring. If the motor fails or something, then automatically the springs close it off, right? So this is how they were able to mitigate this particular problem in the Toyotas. So this is what we call as functional safety. Of course, there is something called SOTIF, safety of the intended function also, which comes into ADAS systems. But I think since there was a question about ASIL, I think pretty nice information for you to have. This is the ASIL analysis. We call it as HARA analysis, HARA, hazard analysis and recommendation, something like that, HARA, or TARA. TARA stands for threat analysis, which is for cybersecurity. Okay, so I think let me stop this with this, right? And let me quickly get back to the questions. Right, so diagnosis is a tool used for recording the error. How can AI be used? Okay, so AI, how you use it here is we are talking about large language models. So large language models need a context. So if you are somehow able to give a context to the large language models, then they can do the reasoning. Since we have some patents pending on it, I don't want to dive too deep into it. But what I can tell you is look up something called MCP. MCP stands for Model Context Protocol. It's like an API. So we are kind of opening up MCPs and API access to cars in a very safe manner so that LLMs can start interacting with them, right? So that's what this basically means. Yeah.
Sajid sir, may I interrupt you for a bit?
Yes, yes, please.
Yeah, give me a moment. Yeah, so before we move on to the Q&A session, I hope my screen is visible.
Yeah, it is.
I'm yeah.
You're visible, yeah.
Yeah. So before we move to the Q&A session, I would really like to thank Mr. Sajid sir for this remarkable and insightful session. Sir, your explanation of EV diagnostics from a traditional UDS-based approach to a modern data-driven diagnostics tech has given us a very clear and practical perspective on how this domain is evolving and what it means for engineering education. Now, I would like to open the floor for question and answer session. Participants are requested to please post their questions in the chat or use the Q&A option. And in order to ensure clarity, we request everyone to please remain on mute. We will take questions one question at a time. Kindly post them in the chat and we will invite you to unmute when it's your turn. Thank you.
So can I go ahead through the question?
Yes, definitely.
Okay. Okay, so Tata Charger showed CX001 Center for Communication error, battery full, etc. Okay, so I mean, I'm not sure about what exactly the PID messages that keep exchanging are. Like I said, every single manufacturer would have their own error codes and PIDs for it. We'll have to refer to that specific manuals. Usually, they don't release it, but if you do have some manufacturers releasing it, so the European vehicles or any vehicle sold in Europe will be covered under something called as RTR, which stands for right to repair. So any vehicle which is sold in Europe, they have to mandatorily release all the service related information. So usually as a part of this error codes are also released. The more important ones are released. But anything in India, Indian manufacturers, good luck trying to reverse engineer them, right? So they don't actually do that. Um, how can you incorporate hardware-based services like ADAS, which are not there in a base model? You're not supposed to tamper with the wiring. Okay, so when you come to an SDV, right? So what happens is the assumption is that all the hardware is already present. So they'll have a camera which is present, but the camera might be working only as a webcam. I mean, as a dash cam. It will not probably implement ADAS algorithms. But if you pay for that specifically, you get ADAS. Like I'll give a very good example, the Tesla Model Y, which is being sold in India right now. I think it sells for about 68 lakh rupees on road. I think they have a showroom in Bombay, if I'm not wrong, right? So that does not come with autonomous driving. If you want the autonomous driving stack, you pay 5 lakhs extra. So which basically means that you can continue driving the vehicle as it is without the autonomous driving stack. But if you want, you pay for it, right? So which basically means it has all the hardware in there, but it's not using it. It is just taunting you, right? It just says that, hey, I'm there. Why don't you use it? Why don't you pay 5,000 a month, 10,000 a month, right? So it's kind of like a hook that people put into it, right? So that's how it works. You cannot retrofit. Some models, some vehicles you can, like Volkswagens, you can retrofit, but we are not talking about that. We are talking about subscription service. Whether data from OBD could be utilized into UTS for retrofit model of EVs. Data from OBD could be utilized into UDS for retrofit. Um, I don't understand how you mean that question, right? So Vijay Kumar, like I'm not able to understand the question. If you could rephrase it, I can probably get back to it. Uh, where do we get this information on STV, DEM, any Google? See, the good thing is AutoSAR is completely open source. So you can just go for search for AutoSAR information on DCM, DEM or something. They'll give you the information. But the problem is this is basically a standards document. So they're going to prescribe how to build it, but it's not going to be explanatory. It's not going to be a textbook. So usually this information you get it when you've worked on it, you understand it. So every single person starts explaining it in their own ways, right? So that's how you get it. But yeah, you can do a Google search. There could be some books on it. You can basically work on that. Next question, can you build a digital twin of an electric vehicle? Definitely, yes, we can. EV diagnostics tool for two, three, and four-wheeler. We'll need to figure out what vehicle that you're talking about. We might have something for some vehicles. We'll probably let you know about that, right? PPT, I'll share it with you, right? We'll share it in the group, and I'll ask my team to basically share it with you. Is there any possible to develop a common diagnostic system easy for service technician of EV? That's a $1 million question right there. So if we can do that, if we can crack it, then it's a startup idea. It's a good thing for research. But a quick answer is yes, you can. Right, you can. How do you develop it? I think that is the IP which sits there. But yes, you can. What is the cost of software? I don't know which software that you're talking about. If it is the UDS stack, then I'll have to check with the team. I'll have to check with the team on the cost, right? So probably we can check it and we can get back to you. Right. So any other questions? Great. Why hybrid vehicle is not famous? I mean, nothing like that. I mean, I would say there has been too much of focus on electric vehicles. But if you look at the number of vehicles which are actually being sold, I'm pretty sure hybrid vehicles sell at least 4 to 5 times more than electric vehicles. Hybrid vehicles still sell a lot more. And you'll see more hybrid vehicles being sold in the future than electric vehicles. It's just marketing, right? So people thought EVs were better, but they are not they are weaponized. So now you'll start seeing a lot of hybrid vehicles coming in. Great. So I think if there's no questions, then I think Ashmita, we can close the session with this.
We just got
Okay.
two more questions. Let's just take that and move
Yeah.
on.
Open source tools for battery management systems. Open source tools. I think there's something called Fox BMS. It's a German repo. Fox BMS should be there. You can probably check that out. Can anything done in UDS to stop fire accidents in EVs, especially thermal runaways? Yes, if you have advanced thermal modeling and if you're able to do that on microcontrollers, you'll have to remember that EVs do not have processors, they don't have laptops in there. You have very small microcontrollers. So if you are able to optimize your compute, if your algorithm is optimized for compute, if it is very efficient, then yes, you can develop algorithms. You'll have to take that into account. It has to run inside a 16-bit microcontroller or a 32-bit microcontroller. Why only batteries are used for energy instead of supercapacitor or hydrogen? Batteries are cheaper right now. I think that's the only thing. Um, Advantage of HEV, it is cheaper than electric vehicles. It combines the benefits of an electric plus IC vehicles. So I think that's the primary benefit that you get from an HEV, right? No range anxiety. You still do get 30, 40 kilometers of pure EV range in modern HEVs. E-waste in the future, absolutely no idea. It's a good question, but no idea. I have no idea. From a sustainability point of view, I have no idea. Is it conversion of IC engine car to EV legal? Yes, I mean you'll have to go get it homologated with the government of India, the RI basically. Some people have done it, but if you want to do it on your own, it is technically not legal. You'll have to take it to RI and you'll have to get it homologated. Any course that you can suggest for our students who wish to become to the field of EV as a fresher? Yes, we do have quite a lot of courses. Probably, Ashmita, you could probably get back to them privately. It's, I think, Miss
Oh, sure.
Bindukala, you can probably get back to them. Can fuel cell vehicles compete with EVs? I think it's just a matter of technology development, right? So, as of now, no. Fuel cell as a technology has not developed, but what will happen in the future, I don't know. I mean, it still remains to be seen, right? So, no idea about that. Great. So, I think we'll close it with this, and probably like any other questions, you can probably privately chat or something, and then we can get back to you with this, right?
Definitely, sir. Definitely. Thank you. Thank you so much, Sajid, sir. As well as thank you all for the engaging questions and discussions. The interaction today clearly reflects the growing interest among faculty in advanced EV diagnostics and real world applications.